Yeah, good evening everyone. So today, as I already shared with Tobias, it's regarding reimagining LLM memory. But how can I reimagine LLM memory, right? So in this case, it's actually learning at the test time. Learning. What does test time means? So if I were to summarize everything in one sentence, it means like learning by doing. Like we all going what we did do every day in our client. For example, we learn and do at the same time. It's the same. So LLMs can or able to inference and change their weight at the same time. Like how? That's where the presentation will go. As a reference, I wanted to shout out to this paper, so end-to-end time training for long contact. It is published by Astra Institute and also big names such as NVIDIA, Stanford, Berkeley, San Diego, and so the why, the problem, right? So if I were to sum up the problem itself, it's two words, like the quadratic bottleneck. What is quadratic bottleneck? So of course you have heard, read the paper called Attention is All You Need. It's about a full attention transformer model that we all know and use today, such as GPT, right? So the problem there is that it requires a full n times n metric to store all the attention relationships. So for every input, for example, if you have 10 input tokens, you have to create 10 by 10. You have 100, it's 100 by 100 metric. So as you can already imagine, it's exponentially exploding. The longer the context, of course, the latency needed is exponentially long, right? There are other intermediate strategies that are used, that are explained in another paper, but they are not there quite yet. So it means that their performance is less than the full attention model. And that's not good because we rather wait a little bit longer rather than getting the wrong answer. But it changed with this paper. So this is the graph. As you can see, with 8K, 16K contact length, the x-axis is the number of input and the y-axis is the latency. So even as you can see, it's not linearly increasing, but it's exponential. So this is the solution that the paper offers. It's called test time training end-to-end, TTT E2E, right? If I were to compare it with what we have right now, I call it the full attention model, just because everything here is transformer already. So this full attention model, first we pre-train, and then we train, and then we fine-tune, and then we freeze the model, bam, and then we deploy, or ChatGPT, OpenAI deploy, or whatever, right? And so if we were thinking to change or fine-tune it further, we can, but it's very sensitive, it's very brittle. I know some of you have tried it before, and if you were try to train it really hard, then it will break. It will give you random output instead, because the model was never planned to be used like that, right? It's never be optimized for stable, fast, adapting kind of thing. So that's not the right way to use it. However, this model is optimized for that. The model treats inference time learning as the training objective rather than just giving back the static answer back. So how? There are two loops here. The first one is the inner loop, learning by reading. So during training, the model processes text as stream. So just streaming text one by one, performing small temporary weight update, and it somehow simulates how the model will adapt in production when it ingests longer document or longer. The second loop is that it teaches to learn efficiently, so that, for example, after the inner loop has been done calculating and adjusting weight, that weights will be used as the initial parameter. So this also simulates a moving target, so that every time the initialized weight is closer and closer to the truth, hence the inference is getting faster and faster. So the shift here is basically shifting from pure pre-training to meta learning. What does it mean? So yeah, as I said before, the goal is not just to encode some knowledge, but to configure the model so that it can learn by doing. Right? It can rapidly internalize this new information as it appears, because it was trained by streaming text, and then it internalized, compress it down into some weight and save it. So it was inspired by human brain. So I believe we can still remember like events that are already past 10 years ago. For example, maybe it's your first time sitting in your data science lecture. You don't remember exactly the details, what does your professor said, what your friend question. However, you still remember the concept. It's the same thing here, but instead of human brain, it's LLM. Right? So how does LLM remember a concept? It's by changing its weight, which I will talk about. Yes. If it's output, say how does it know the target? During training, you should know what the target is, or by streaming, right? The target would be the next predicted token. Not during endurance. Right, right. But really good contact. But in this case, the training and inferencing, because as I said before, this is TTT model, so you also change weight during inferencing. There is it where the second loop comes into place, where the weight itself will change over time. So of course, depending on what you give, like your chunks, your documents, it can change the weights, right? For example, if I were to ask, hey, what should I drink today? Because I were asking a lot of tea related question yesterday, it will answer, hey, you should drink tea today. Whereas if your model, if you have asked regarding coffee a lot in the past recent days, it will answer coffee to you. So that's where I think the revolutionary, the innovation here comes. So how does the TTT architecture looks like? There are three new concepts here. Well, not actually new concept in this paper. However, it's at least different from the full attention model. The first one is the sliding windows attention. Instead of full attention, like what I told you in the start, the SWA actually restrict attention to limited fixed size windows of recent token. The advantage there is of course speed, right? No matter how big the document you give the LLM, it will create a constant, it will use a constant or read a constant chunks, so that at the end of the day, the latency is also constant. Targeted wave update for adaptation. So the full attention transformer, it throws all the weight. But in this architecture, TTT architecture, the researcher actually let the final 25% of the MLP model, like the layers, they let it mutable, changeable, shiftable, right? So it does not freeze all the time. That's what makes it able to change or shift answer during inferencing. So why the last 25%, right? As we already know, this elasticity can be compared to our neuroplasticity in the brain. So the more elastic it is, the higher the percentage here, the more the model can remember from the past context. It turns out that the researcher did ablation test or brute force attack, I would say, on the x-axis. Sorry that I kind of cropped the unit. It's actually the delta loss. So for example, here, if you compare delta loss full attention with full attention, you get 0. And 0 is basically the gold standard here. And everything else here is below 0. And below 0 is actually better because the delta loss means that the lower, the better. As you can see here, the worst part is the TTT1 layer. And you know, that's why the next best one, the next worst one is the TTT3 layer. And if you see it, the 6th and the 12th layer here is somewhat similar in terms of delta loss. So the researcher decided that, hey, we should just stick to 6th layer. And 6th layer in this case translates to 25% because at the end of the day, they created, their model is 24 layer model. So 6 translates to 25%. And as we probably know as well, the more layers that we don't fix means that it also makes the computational cost higher as well. So they think of that trade-off. They decided like, yeah, 6 layers or 25% is the best. And the third one is the dual stack storage or dual track storage. So okay, we have a pre-trained LLM, and this pre-trained LLM has been given a lot of good knowledge, right? Clean knowledge such as books, such as, I don't know, whatever the internet offers, and it already contains some sort of truth by itself. So the researcher here created a static MLP just to remember, hey, what you remember in pre-training, don't forget it. However, it creates a second parallel MLP or multi-layer perceptron, so that the model is able to shift based on the input that it received from the user. So here, this is the model, how it looks like. If the arrow up shows the forward propagation, and the arrow down shows a back propagation, right? So the first one, it goes up. X1 is the input. So for example, if you have a document, you can imagine that as a string of input, right? It goes up, and then it predicts something, so P2, and then it got the loss function, and then because from the loss function, it can go down to actually calculate the backprop, and in the backprop, it changes here the MLP, the multi-layer perceptron. So the weights have been changed there, and then therefore, when the user add or ask the second question, hey, how about this document, or give another prompt, it goes again to forward propagation, get another prediction. However, this MLP from the first loop, let's say, is affecting the answer here, more or less. That's how it goes. So before we continue to the result, I want to give some honorary mentions to the previous work. The first one is the sliding windows attention. Second one is Mamba 2 and gated delta net, and the third one is TTT KVM. All of these models, they are quite similar to our model. Just treat them like our stability. The differences, of course, can be read more in detail in each of their parts. So the experiment result, right? If you can see here on the top left, you see there are some nice looking graphs. The first one is, I want to talk about the left part first. So the y-axis here is the loss delta with full attention. So again, the lower the better. And and the x-axis here is the context length. So please focus on the orange part first, because orange part is the transformer with full attention. As you can see, it's just constant. It's just constant 0, right? The second one is our model, which is the blue one here. The blue one is also constant. What does it mean? It means that, hey, even if the user gives longer and longer context, it doesn't bother our model anymore. It will just, the loss will be just constant, and added the cherry on top, our model performs better than the full attention model, which is the standard nowadays. So it's a green, right? Compared to the other models, so for example, they are going up. So, and all of these models are actually quite powerful, like the Mamba 2, gated delta net, like all of those are very powerful. However, our model is better in bigger context length, right? So let's talk about the second graph here, which is the latency versus the context length. So latency, again, the higher it is, the worse it is, because the user have to wait longer, right? As you can see here, something explodes, which is the full attention model. It goes up, and then in a exponential way. However, all other models, as I said, also they are quite powerful. They are constant, which is what we want. Like the longer the context length, it should be still fast enough for the user not to wait for 30 seconds. And that is, these two are the reason why I really like this paper. The reason why I think this paper can be, or this paper is the first time that it both better in terms of perplexity, and second, really constant in terms of latency. However, this paper also has some limitation, right? The limitation, first limitation is lacking in searching for needle in high. So it means that it's not good with detail. If you ask how many Steven in document ABC, like it's bad. I mean, maybe I'm giving a bad example as well, but you know what I mean. It's not good in the like reading the detail, and that's also what we have thought from the start. That's our intuition from the start, right? So by this model is really compressing all the knowledge into weights, some little weight that's shifted here and there a bit, and it's not good for remembering all the detail. For that one, the normal RAG is the way to go. Second, training is complicated. Of course, training is complicated because it requires two loops, right? The loop, the inner loop, the outside loop, and both have to be calculated. The gradient, for example, gradient, and so on and so forth. So let me check my note. At 8K, so 8K context length, our model is 3 times, or 3.4 actually, 3.4 times lower to train than the full attention. This is the training, not the inference, right? And then on the larger model, so 120K model, the difference is not so, like less. The difference is 1.2 times, but still, it's still lower, longer to train. So for future work, we suggest to custom another kernel to support the second order gradient better. So from a pre-trained transformer to reduce the training time for TTT model. And this one is not mentioned in the paper, but I think the monitoring of this model is going to be a headache, because as you might know, like the model is changing every time we talk with it, we use it. So when it comes to benchmark, how can we benchmark things that are, keep changing over and over again? When we change the order of the question, it will also change the model. So it's going to be a headache as well. But in the future, I think this is just the beginning of the long range memory. I would say there are 3 types of memory now. We have the short range, which is the high fidelity window attention mechanism kind of thing, the normal LLM that we have right now. We have external knowledge such as RAG databases that can be retrieved once we need it. However, I think there is this new concept of this long range large compressed memory, which I think is cool, and people will use more and more. So after listening to my presentation today, don't remember all of my word for word, but remember the gist of it, the way the researcher got to this model, what inspires them, and remember that in the future maybe there's this long range compressed memory or TTT mechanism more and more in our life. Right, with that being said,